Hello, and welcome to the Educational Lecture Series supported by the TEAM-NANO European Horizon program. In this lecture series, we focus on the fundamental concepts in electrochemistry. I am Dr. Evangelia Founta, and I'm a research fellow at the University of Southampton. We will focus on electrochemistry applications in energy, with specific focus on batteries, and we will then move to uncover the underlying electrochemistry concepts that govern these and more systems. We will first put our focus on the applications in the energy section. And here, let's pose the first question. What is the main power source that comes to your mind when we talk, for example, for a laptop or for a phone? The answer is batteries. Batteries are one of the most important technologies that power modern life. Their core batteries are energy storage devices that convert chemical energy into electrical energy. But first, let's ask, why do batteries even matter? Many energy sources are either intermittent or not portable. For example, renewable energy sources like solar and wind can only generate electricity under certain conditions. On the other hand, batteries allow us to store energy and use it later, making energy available whenever and wherever it is needed. Because of this capability, batteries have enabled many technologies that define modern society. And that is portable electronics, that we briefly mentioned, such as smartphones, laptops, and wearable devices, which rely entirely on energy storage. Batteries have also enabled the growth of electric vehicles, of course, in the modern society. They are used across a huge range of applications, from consumer electronics and medical devices to robotics, transportation systems, and grid-scale energy storage. And that is overall to say that in many ways, batteries are the key technology that allows electricity to become portable and reliable. Now let's move a little bit on some history facts, a bit of history lessons. So the history of batteries begins in the early 1800s with the Italian physicist Alessandro Volta. Volta developed the first true electrical battery known as the voltaic pile. The voltaic pile consisted of alternating discs of two different metals, and that is zinc and copper, separated by pieces of cloth that were soaked in an electrolyte solution, which was typically brine. This arrangement created a continuous electrochemical reaction that produced a steady flow of electrical current, something that had never been achieved before. And this invention was revolutionary because for the first time, scientists had a reliable and controllable source of electricity. Volta's work was so significant that he was invited to demonstrate his invention to Napoleon Bonaparte, actually, who later honored him for this breakthrough. And the voltaic pile, as a result, paved the way for the entire field of electrochemistry and modern energy storage. Now we move on to do a classification of batteries, and one of the simplest ways to classify batteries is by asking a key question: can the battery be recharged after it's used? Based on this, batteries are divided into two main categories: primary batteries and secondary batteries. So primary batteries are non-rechargeable. In these systems, the electrochemical reactions that produce electricity are essentially irreversible, meaning that once the chemical reactants are consumed, the battery can no longer deliver power. Common examples include alkaline batteries, which are widely used in household devices like remote controls and flashlights, and then lithium metal batteries, which are often used in devices requiring longer shelf life, such as medical implants or sensors. On the other hand, secondary batteries are rechargeable. In these batteries, the electrochemical reactions that take place can be reversed, allowing the battery to be used many times. Some examples include lead-acid batteries, commonly used in car starter batteries, and lithium-ion batteries, of course, which power most modern portable electronics and electric vehicles. Essentially, this distinction between primary and secondary batteries is fundamental because it determines how the battery is used, its lifetime, and its role in different technologies. Now let's take it from the last mentioned lithium-ion batteries and put the focus there, as lithium-ion batteries are the modern pillar of our society. It is one of the most important developments in modern energy storage, as this technology has become a cornerstone of portable energy because of the unique properties of the lithium elements. Lithium is the lightest metal in the periodic table, and as a result, lithium-ion batteries are characterized by high energy density. So what is that? It means that a large amount of energy can be stored in a relatively small and lightweight device. And this is why lithium-based batteries are ideal for applications where weight and size are crucial, such as smartphones, laptops, and electric vehicles. The development of lithium-ion batteries. So this was not a single discovery, but rather a sequence of breakthroughs between the 1970s and mid-1980s. In the 1970s, first, Stanley Whittingham developed one of the first lithium rechargeable battery concepts, using lithium metal and a titanium disulfide cathode. Later in the 1980s, John Goodenough discovered lithium cobalt oxide as a cathode material, which significantly increased the battery voltage and energy density. Soon after, Akira Yoshino developed the first practical lithium-ion battery using a carbon-based anode instead of lithium metal, which greatly improved the safety and stability of the system. These contributions together established the foundation of the lithium-ion batteries we use today. And in recognition of this transformative work, Whittingham, Goodenough, and Yoshino were awarded the 2019 Nobel Prize in Chemistry. After that, the technology was commercialized in 1991 by Sony, marking the beginning of a new era of portable electronics. Now, to better understand how batteries work and how their performance is evaluated, it is useful to introduce a few key terms that are commonly used in battery science. So the first one is charge. Charging a battery means essentially supplying electrical energy to the system, which drives electrochemical reactions that store energy inside the battery in a chemical form. The opposite process is, of course, discharge. During discharge, the stored chemical energy is converted back into electrical energy, which then powers an external device, can be our phone, for example. Another important concept that we're looking for when we buy a battery is capacity. So capacity essentially describes the total amount of charge that a battery can store and deliver, and it is usually expressed in milliampere hours or mAh. In simple terms, a higher capacity means the battery can power a device for a longer period of time before needing to be recharged. Closely related to that comes cycle life. So cycle life refers to the number of complete charge and discharge cycles a battery can undergo before its capacity significantly degrades. Over time, it is given that all batteries gradually lose their ability to store energy, which limits their usable lifetime. To make this more concrete, as an example, we can look at the batteries used in smartphones as an example. Even within the same generation of phones, different models often have different battery capacities, and of course the price is adjusted based on the higher capacity that you can get from a battery. For example, the basic model of the same series of phones that is currently on the market typically has the smallest battery capacity, around 3,692 mAh. The Pro version is slightly larger, and the Pro Max version at the largest capacity, allowing it to operate longer between charges. This illustrates how battery capacity directly influences the runtime and performance of electronic devices, which is why improving battery capacity and lifetime is a major goal in battery research and development right now. So now let's dive a bit deeper into the insides of a lithium-ion battery to understand how it works. Yes, you see a sandwich in the slide, it's not wrong, so this is to help you imagine the battery structure as a sandwich. So essentially each layer of the sandwich represents a different component of the battery. So let's start from the top slice of the bread. The top layer represents the aluminium current collector. In a battery, the current collector is a conductive metal sheet that gathers and transports the electrons that are generated during the electrochemical reactions. So in this case, aluminium is used on the cathode because it is lightweight, highly conductive and stable at the operating voltages of the battery. A good real-life example of aluminium is aluminium foil. It's the same material we commonly use in kitchens for wrapping food. Just below that comes the cheese layer, which represents the cathode material, often lithium cobalt oxide, but it's not limited to that, can be other materials as well. The cathode is one of the main active materials in the battery, and it is where lithium ions are stored when the battery is discharged. Lithium cobalt oxide is widely used in many consumer electronics because it can provide high energy density. Cobalt is one of the key elements in this material, and it is mined in several regions of the world, but with a large portion of it coming from the Democratic Republic of Congo. Beyond batteries, cobalt is also used in superalloys for aircraft engines and high-performance materials. So next in the sandwich comes the lettuce layer, which is moistened with mayonnaise, which represents two important components, the separator and the electrolyte in the battery. So the separator is a very thin plastic membrane, usually made from polymers such as polyethylene or polypropylene. Its role is very crucial as it actually separates the cathode and the anode electrically, so they do not touch and cause a short circuit, while still allowing lithium ions though to move through it. The electrolyte, which we can think of as a mayonnaise soaking the lettuce, it is a medium that allows lithium ions to move between the electrodes during charging and discharging. In lithium-ion batteries, the electrolyte is typically a liquid solution containing lithium salts dissolved in organic solvents. The word electrolyte might sound familiar from sports or gym drinks, which contain electrolytes like sodium or potassium ions to hydrate. In both cases, electrolytes are substances that contain mobile ions and allow the transport of charge. So moving further down the sandwich, we reach the turkey slice, which appears to be the anode, typically made of graphite. During charging, lithium ions move from the cathode and are stored between the layers of graphite in a process called intercalation. Graphite is actually a very familiar material. It is the material found in the tip of the pencil. Finally, the bottom slice of bread represents the copper current collector. Just like the aluminium current collector on the cathode side, copper serves as a conductive pathway that collects and transports electrons. Copper is a very commonly used metal. It is used on the anode side because it's highly conductive and chemically stable at the lower voltages of the anode. A simple everyday example of copper use is coins or electrical wiring in buildings, for example. So when we assemble all of these layers together, we obtain the internal structure of a lithium-ion battery. So now that we have introduced the battery as a sandwich structure, let's connect this analogy with what actually happens inside the lithium-ion battery during operation. So let's say I tilt this to make it actually parallel with the inside of the lithium-ion battery. So what happens is that during operation, lithium ions move back and forth between the cathode, the cobalt oxide cathode, and the graphite anode, while electrons travel through the external circuit to power our devices. So you say that during discharge, the battery is powering the device. Lithium ions move from the anode, which is graphite, to the cathode through the electrolyte and across the separator. At the same time, the electrons cannot pass through the separator, so they travel through the external circuit, for example through your phone or laptop, where they provide electrical power. After passing through the device, the electrons return to the cathode side of the battery. Now let's look at what happens inside the materials themselves. So at the anode, lithium is stored inside the layered structure of graphite. Graphite actually consists of many stacked sheets of carbon atoms, graphene layers arranged in hexagonal layers. These layers create small spaces between them where lithium ions can be inserted and stored. This process is called intercalation, which simply means inserting ions into the structure of materials without destroying the framework. When the battery discharges, lithium ions leave the graphite layers in a process called deintercalation. They move through the electrolyte and are then inserted into the crystal structure of the cathode material. When we charge the battery, the process is reversed. An external power source pushes electrons back through the circuit, forcing lithium ions to move from the cathode back to the anode, where they are once again intercalated between the graphite layers. This reversible movement of lithium ions between the two electrodes is what makes lithium-ion batteries rechargeable, and that is why we call these type of batteries rocking chair batteries. In the real battery, those sandwich layers that we saw are stacked many times and tightly rolled to maximize the surface area. The cathode, separator and anode form repeating layers with the aluminum and copper can collectors attached to carry electrons in and out of the battery. Now we will move on to uncover the underlying electrochemistry concepts that essentially are governing battery behavior, but it's not only limited to batteries. So what is electrochemistry? Electrochemistry is the field that studies how chemical reactions and electricity are connected, and especially how chemical energy can be converted into electrical energy and vice versa. This principle forms the foundation of many important technologies. For example, batteries store and release energy through electrochemical reactions, as we previously saw. Supercapacitors, on the other hand, are energy storage devices that store electrical charge at electrode surfaces to deliver power very quickly. Fuel cells are another class of energy storage devices, and they convert chemical fuels, such as hydrogen, directly into electricity through electrochemical processes. As I said, electrochemistry is not only limited to energy storage, it is also widely used in sensors, for example, where electrochemical reactions help detect specific chemicals, and also in understanding and preventing corrosion, which is essentially an unwanted electrochemical reaction that degrades metals. And because of these applications, electrochemistry plays a key role in energy technologies, environmental monitoring, material science, and industrial processes as well. So to understand modern electrochemistry and energy storage, it is useful to look briefly at how the field developed over time. The history of electrochemistry can be divided into several key phases, each marked by important discoveries and scientists. So the first phase is origins and discovery between about 1780 and 1835. This period began with Luigi Galvani, who discovered that electrical effects could cause muscle contractions in frog legs. He proposed the idea of animal electricity. Although this interpretation was not entirely correct, his experiments revealed a fundamental connection between electricity and chemical systems. Soon after, Alessandro Volta demonstrated that electricity could be generated by chemical reactions between different metals. In 1800, he invented the voltaic pile, the first true battery, which provided a continuous and controllable source of electric current. This discovery essentially launched the field of electrochemistry. So the next phase is the foundation period from about 1835 to 1870, represented mostly by Michael Faraday. Faraday established the laws of electrolysis, which quantitatively describe how electrical current drives chemical reactions. He introduced key concepts such as electrode, anode, cathode, ion, and electrolyte terminology that is still used today. His work created the first quantitative framework for electrochemistry. Then moving on to the third phase, it is ionic theory and thermodynamics, roughly from 1870 to 1910. During this time, scientists began to understand how ions behave in solution. Svante Arrhenius proposed that electrolytes dissociate into ions when dissolved in water. Wilhelm Oswald helped develop the theory of ionic equilibrium and chemical kinetics in solutions. And finally, Walter Nernst introduced the Nernst equation, which links electrode potential to concentration and temperature, forming the thermodynamics basis of electrochemistry. The next stage is kinetics from around 1900s to 1950. While thermodynamics tells us whether a reaction can occur, kinetics describes how fast it happens. Max Vollmer and John Alfred Valentine Butler developed the Butler-Volmer equation, which describes the relationship between current and electrode potential in electrochemical reactions. During this period, Jaroslav Hierovsky also introduced polarography, an important electroanalytical technique that helps study electrochemical reactions. The following phase is electron transfer in modern theory from about 1950 to 1980. So during this period, scientists began to understand the microscopic mechanisms behind electron transfer reactions. So Gilbert Lewis helped establish modern concepts of chemical bonding and electron transfer. Later, Rudolf Marquez developed Marquez theory, which explains essentially how electrons move between molecules during redox reactions. This work earned him the 1992 Nobel Prize in Chemistry. And finally, we reach the energy storage revolution from around 1970 to today. So during this period, electrochemistry became central to modern energy technologies. Stanley Whittingham, John Goodenough, and Akira Yoshino developed the foundations of the lithium-ion battery, as we mentioned previously, which now powers most portable electronics and electric vehicles. And for this work, they were awarded the 2019 Nobel Prize in Chemistry. So now we move on to the heart of electrochemistry. So electrochemical systems are fundamentally based on redox reactions, which stand for reduction and oxidation. So these reactions involve the transfer of electrons between chemical species. One substance loses electrons, while another gains electrons. And because electrons cannot simply disappear or appear, oxidation and reduction always occur together. Reduction is the gain of electrons, and oxidation is the loss of electrons. So, for example, a zinc ion can gain 2 electrons to form metallic zinc. In this case, zinc ions gain electrons, so they are reduced. In the case of oxidation, a nickel atom can lose 2 electrons and become a nickel ion. Here, nickel loses electrons, so it is oxidized. So redox reactions are not only important in batteries and electrochemical devices, they are actually everywhere in nature as they are fundamental processes in chemistry, biology, and energy systems. So let's look at 3 common examples. The first example is iron rusting. So when iron is exposed to oxygen and moisture in the air, it gradually forms rust, which is mainly iron oxide. In this process, iron atoms lose electrons and are oxidized, forming iron ions. At the same time, oxygen molecules in the presence of water gain electrons, meaning they are reduced. The result is the formation of iron oxides, which appears as the reddish-brown rust we see on metal surfaces. A second example is photosynthesis, the well-known process that plants use to convert sunlight into chemical energy. So during photosynthesis, plants use light energy to transform carbon dioxide and water into glucose and oxygen. So in this process, carbon dioxide is reduced, meaning it gains electrons, and is converted into energy-rich organic molecules like glucose. Meanwhile, water molecules are oxidized, releasing electrons and producing oxygen gas. This redox process is fundamental for life on Earth because it produces both oxygen and the organic molecules that form the basis of the food chain. The third example is combustion, such as when we burn fuels like wood, gasoline, or natural gas. In combustion, the fuel reacts with oxygen in a redox reaction. So the fuel molecules lose electrons and are oxidized, while oxygen, on the other hand, gains electrons and is reduced. This reaction releases large amounts of heat and energy, which is why combustion is widely used for heating, transportation, and energy production. So an important concept in electrochemistry that has been already mentioned as a term is the electrochemical potential. So the electrochemical potential is essentially the difference in electrical potential between the 2 electrodes in an electrochemical cell. So this we call the cell potential. So in simple terms, it tells us how strongly electrons are driven to move from one electrode to the other. So this potential difference is measured in volts. 1 volt is defined as 1 joule of energy per coulomb of charge. And this means that the voltage of a cell represents the amount of energy available to move electric charge through an external circuit. Now let's look at the electrochemical cell shown in this diagram here, which again consists of a zinc electrode and a copper electrode, each immersed in their own electrolyte solutions and connected by a salt bridge. So a salt bridge connects two half cells, allowing ions to flow, but prevents mixing of the electrolyte solutions. So at the zinc electrode, oxidation occurs. So zinc metal is losing electrons and enters the solution as zinc ions. This reaction releases electrons into the electrode, making zinc the anode. So at the copper electrode, reduction takes place. So copper ions in solution gain electrons and deposit onto the electrode as solid copper. This electrode is therefore the cathode. These two reactions are called half reactions because each describes only one part of the overall redox process. The overall chemical reaction in the cell is simply the combination of these two half cell reactions. So each half cell reaction has an associated electrode potential, which reflects the tendency of that species to gain or lose electrons. So in the example shown, zinc has a standard potential of minus 0.76 volts, while copper has a standard potential of 0.34 volts. The difference between these two values gives the cell potential, which in this case is approximately 1.1 volts. So this potential difference is what drives the flow of electrons through the external circuit, allowing the electrochemical cell to generate electrical energy. Now, in order to understand why certain electrochemical reactions occur more easily than the others and explain this tendency terminology, the concept of the standard electrode potential is introduced here. So the standard potential represents the tendency of a chemical species to gain electrons and be reduced under standard conditions. So what do standard conditions mean? They are typically 25 degrees Celsius temperature, 1 atmosphere pressure, and a concentration of 1 molar for dissolved species. So these standard potentials are measured relative to a reference system, known as the standard hydrogen electrode, which is assigned a potential of 0 volts. The key idea here is that the potential at which electrochemical processes occur are directly linked to the standard potentials of the chemical species in the system. So by comparing these values, we can predict whether a reaction is thermodynamically favorable. So the diagram shown here is called the Electrochemical Series, which lists different half reactions along with their standard potentials. So at the top of the table, we find species with very positive standard potentials, such as fluorine or oxygen. These species have a strong tendency to gain electrons, meaning they are strong oxidizing agents. At the bottom of the table, we find species with very negative potentials, such as lithium or magnesium. So these elements easily lose electrons, making them strong reducing agents. So this difference in reduction potentials is what allows electrochemical cells to generate electricity. When two species with sufficiently different potentials are paired together, electrons naturally flow from the species that prefers to lose electrons to the one that prefers to gain electrons. For example, lithium, that is central to this lecture series, has one of the most negative standard potentials, which explains why it has powerful anode material properties in lithium-ion batteries. So the electrochemical interface has been briefly mentioned in the previous slides, as it is one of the most important regions in any electrochemical system. It is essentially the boundary where the solid electrodes meets the electrolyte that can be aqueous or non-aqueous, for instance. Although it may look simple, this region is actually highly structured and plays a critical role in electrochemical reactions. So the illustration here shows what is known as the electrochemical double layer. Let's start with the metal electrode shown on the left. So because the electrode can store electronic charge, it can develop either a positive or negative surface charge depending on the applied potential. Here the electrode surface is positively charged. So as a result, oppositely charged ions in the electrolyte are attracted towards the electrode surface. So these ions arrange themselves very closely to the electrode, forming the first part of the double layer. This region is called the Helmholtz layer. It consists of ions that are strongly attracted to the electrode surface and form a relatively compact layer. In a sense, it behaves somewhat like the plates of a capacitor with opposite charges facing each other across a very small distance. So beyond this compact layer, the electrolyte still contains ions that are influenced by the electric field from the electrode, but they are not tightly bound to the surface. Instead, they are distributed more gradually in the solution. So this region is called the diffuse layer. In the diffuse layer, ions move continuously due to thermal motion and diffusion, but their distribution is still influenced by the electrical field generated at the interface. Together, the Helmholtz layer and the diffuse layer form what we call the electrochemical double layer. This structure is extremely important because it is where electron transfer reactions occur, where ions accumulate before reacting, and where charge is stored at the electrode surface. In fact, this interfacial region controls many key electrochemical processes, including reaction kinetics, capacitance, and charge transfer efficiency. To continue the discussion on the electrode-electrolyte interface, for the redox reaction to take place, the electroactive species have to first reach to the interface and then undergo the electrochemical reaction. So mass transport describes how these electroactive species, such as ions or molecules involved in the redox reactions, travel from the bulk electrolyte towards the electrode surface where the reaction occurs. There are three modes of mass transport. So first, there is diffusion. So diffusion is the movement driven by a concentration gradient with a diffusion coefficient d. Second is electromigration, which is essentially the movement caused by an electric field, where phi is the electric potential. And finally, convection, that is the movement caused by fluid motion with a velocity v. So in electrochemistry, this mass transport is generally described by the Nernst-Planck equation, which gives the molar flux of an electrochemical species denoted as J. So the molar flux essentially represents the amount of substance that passes through a unit area per unit time. So the Nernst-Planck equation describes the three mass transport mechanisms that we mentioned previously, and that is diffusion, migration, and convection. So in many conventional electrochemical systems, particularly near the electrode-electrolyte interface, described by the Gui-Chapman and Stern models, mass transport is dominated by diffusion. And this happens because the supporting electrolyte in the solution usually suppresses migration effects, and in many experiments there is no steering of the solution, and the solution is kept still, minimizing convection. As a result, the Nernst-Planck equation can often be simplified to describe pure diffusion, which is expressed by Fick's first law. So Fick's first law states that the flux of a species is proportional to the concentration gradient. The negative sign indicates that the species move from regions of high concentration toward regions of lower concentration. In practice, in electrochemical systems, this means that when reactants are consumed at the electrode surface during a reaction, their concentration near the electrode decreases, and this creates a concentration gradient which drives new species from the bulk of the solution towards the electrode that is lower concentration by diffusion. So understanding in general these transport processes is essential because mass transport can often limit the rate of electrochemical reactions, especially at high current densities. So now let's move on to the electrode cell where we perform electrochemical experiments in Practical lab setups. So we often use a setup known as the 3-electrode cell, and this configuration allows us to accurately control and measure the potential of an electrode while monitoring the resulting current. So the system consists of 3 electrodes: the working electrode, the reference electrode, and the counter electrode, each with a specific role. So the working electrode is where the electrochemical reaction of interest takes place. This is the electrode whose behavior we actually want to study. So for example, in batteries, this can be the material being tested for energy storage. In sensing applications, this can be the surface where the analyte reacts. Then the reference electrode provides a stable and well-defined potential against which the working electrode potential can be measured. Ideally, the reference electrode does not pass current, which allows its potential to remain constant throughout the experiment. Some common examples include silver-silver chloride electrodes or saturated calomel. Finally, the third electrode is the counter electrode, sometimes called the auxiliary electrode as well. So the role here is to complete the electrical circuit and carry the current generated during the experiment. The counter electrode typically uses an inert and conductive material such as platinum, so that it does not interfere with the reaction going on at the working electrode. So this 3-electrode configuration is widely used in electrochemical measurements and research, including techniques such as cyclic voltammetry, chronobarometry, and impedance spectroscopy, which we will analyze further in part 2 of this lecture series. It is also commonly used in the study of batteries, fuel cells, corrosion processes, and electrochemical sensors. There are also a few practical considerations when setting up a 3-electrode cell. So for example, the reference electrode should be placed close to the working electrode to minimize potential errors caused by solution resistance. Otherwise, the solution resistance has to be compensated using the tool-specific function. And finally, another important practical point is that size matters in this case, as the counter electrode should generally have a much larger surface area than the working electrode, at least 3 to 10 times larger, as this ensures that the current density at the counter electrode remains low, preventing it from becoming the limiting factor in the experiment and helping maintain stable measurements. So aside from the 3-electrode cell, a 2-electrode setup can be used. So each one serves a different purpose depending on what we want to measure. So the 3-electrode configuration is typically used in fundamental electrochemical studies, and as we discussed earlier, it consists of a working electrode, a reference electrode, and a counter electrode. So the advantage of this setup is that it allows us to precisely control and measure the potential of the working electrode relative always to a stable reference electrode. It makes it ideal for studies where we want to examine the intrinsic behavior of a specific material or reaction, for example, a half-cell reaction. So, in contrast, the 2-electrode configuration is closer to how a real electrochemical device operates. So in this case, the system has only 2 electrodes, a positive and a negative. The voltage is applied across 2 electrodes, and the measured current reflects the behavior of the entire cell rather than a single electrode. So because of this, 2-electrode setups are commonly used when testing complete energy storage devices such as batteries and supercapacitors, where we're interested in the overall performance of the cell. So as you see here, this is not a classic beaker/vial configuration. So in addition to that classic configuration, another common setup used in battery research is the Evangelia cell. So these cells provide a practical and controlled way to build small experimental battery systems. So a Evangelia cell is a compact sealed electrochemical cell that uses fittings to compress the different components together. So inside the 3-electrode cell, we typically place 2 electrodes separated by 2 separators for electrical isolation, which in turn sandwich the reference electrode in between. The remaining space is filled with the electrolyte solution and the cell is sealed. Contrary, in the 2-electrode cell, the 2 electrodes are separated by a separator soaked with electrolyte, forming a small battery-like structure. So Schweizerloch cells are widely used in battery and supercapacitor research because they offer several advantages compared to open beaker/vial systems. They are more mechanically stable, they allow good electrical contact between components, and they can be easily assembled and disassembled to test different materials. Finally, they also help minimize electrolyte evaporation and contamination, which is particularly important when working with sensitive electrolytes or air-sensitive materials. To control these electrochemical experiments, we use specialized instruments called potentiostats and galvanostats. So in practice, most modern instruments are actually combined potentiostats/galvanostats, meaning they can operate in either mode depending on the experiment. So a potentiostat controls the potential of the working electrode relative to the reference electrode while measuring the resulting current flowing through the cell. This is the most common mode used in electrochemistry, especially for techniques such as cyclic voltammetry, for example. So a galvanostat, on the other hand, operates in constant current mode, and instead of fixing the voltage, the instrument applies a constant current, and the potential of the system is measured as it evolves. This mode is commonly used in battery charge and discharge testing. Modern instruments, though, can switch between these two modes, which is why they're typically referred to as potentiostats/galvanostats. Now let's briefly look at how the potentiostat works using the diagram shown here. So at the core of the instrument, there's a high-gain operational amplifier, which acts as a feedback controller. Thus the user sets a desired potential set point, and the instrument continuously compares this value with the actual potential measured between the working electrode and the reference electrode. So if the measured potential differs from the set point, the instrument automatically adjusts the voltage applied to the counter electrode. So this feedback loop continues until the potential of the working electrode matches the desired value. In this system, the reference electrode acts purely as a voltage sensor, meaning it measures potential but carries almost no current. The counter electrode supplies the current needed to balance the electrochemical reactions occurring at the working electrode. The current flowing through the working electrode is then measured by the instrument, allowing us to study how the system responds to controlled electrochemical conditions. Thank you for attending the first part of the lecture series. Please continue to part 2 of this series to learn about electrochemistry, practical methods, and applied examples.